Okay, in class I had students do this without my help, but let's see if we can do this kind of quickly together. We want to sketch the polar graph below its rectangular counterpart. So here we have y equals 2 sine of 2x. Here we have polar r equals 2 sine of 2 theta. 2 sine of 3x, 2 sine of 3 theta. And then we have 4x and 4 theta and 5x and 5 theta. Now basically the idea here is we have the same relationship between A and the length of the petal and B and the number of petals as we did in cosine. The only difference is the symmetry. We don't have the first petal on the horizontal axis with a symmetry that revolves around the angles 0 and pi. We're going to have a symmetry that revolves around the angles pi over 2 and 3 pi over 2. But our angle does not start at pi over 2. It starts somewhere in between, our first petal somewhere in between 0 and pi over 2. So we have to figure out where it starts and why. So let's take a look at the high points of the graph to find where the tips of the petals are. So here's for 2 sine of 2x. We have a tip of the petal here halfway between pi over 6 and pi over 3. So this would be at pi over 4. So pi over 4 we have positive 2, pi over 4 positive 2. Then halfway between 2 pi over 3 and 5 pi over 6 right here, we're at negative 2. So that means I have to go the opposite direction. Okay, so that takes me over into quadrant 4. Now we're at halfway between 7 pi over 6 and 4 pi over 3. We're at this angle right here. Now we're at positive 2 again. So that would be right here. And then at halfway between 5 pi over 3 and pi over 6, we're at negative 2 again. So now we're back over to here. So basically, every time we go from one high point to the other, we have to, of course, cross through 0. So we start at 0 because we have the 0, 0 here. So we start at 0. We swing into quadrant 1. Then we ended up, when we went to quadrant 2, we're in negative. So now we're swinging into quadrant 4 with our negative r value from quadrant 2. Now we're back up to positive r values in quadrant 3. Then negative r values in quadrant 4, which swings us into quadrant 2. So this is what the graph looks like. So the angle of the first petal here in quadrant 1 is pi over 4. Now let's do this next one. This one starts at 0, 0, and I made all of these go out to 2 just to keep it simple. So now our high petal is at pi over 6. So we've got one at pi over 6. Then we're down here at pi over 2. We're negative. So that bumps us down to 3 pi over 2. So this was, if we were to number this, here's number 1, here's number 2. So number 1 was here. Here's number 2. Number 3, we're at 5 pi over 6, 2. So here's number 3. Then we're at 7 pi over 6, negative 2. Well, 7 pi over 6 is over here. So 7 pi over 6, negative 2 gets us back over to where we started from on 1. So this repeats back to this one. When we get to, I'm sorry, not that one. This one repeats back to this one. This one repeats here is 3 pi over 2, positive 2 is the same thing as pi over 2, negative 2. So this one repeats back to this one. And then the last one right here, 11 pi over 6, negative 2, repeats back to this one. So we end up, that's kind of crazy looking. I'm not sure that I really like that. Maybe a better way to be doing this, I think I like it. A better way to be doing this would be if I continued to number these. This would be 4, 5, and 6. So we'd end up here with 4, 5, and 6. Oops, wrong way. 4, 5, and 6. So we start at the center, we go out to to number 1, then we go down to number 2, then we go to number 3, and then it starts over again, and we would go to 4, and we would go to 5, and we would go to 6, and we'd end up back at the origin. So that's what this would look like. Now where the first petal starts here is pi over 6. Okay, so notice here's pi over 6, here's pi over 4. Now what does this one look like? So this one's a little weirder because I can't really tell where that one is. You know, just from this grid it doesn't look terribly good. So I do see that I'm at 0 here at pi over 2. Where in the world are these going to be? Okay, this is a little trickier. So I know that my 0 points are at pi over 2 and at pi and at 3 pi over 2 and at 2 pi. I'm going to have to come back to this one. So let's abandon that one for a moment, and maybe also this one. What am I going to do? I'm going to have to look at these on a calculator and figure out what they sort of look like, and then maybe go back and try to figure out what these angles are. Okay, so where is that angle of the first petal? So let's use Desmos, and let's do r equals 2 sine of 4 theta and 2 sine of 5 theta. Okay, so let me just kind of get rid of these here. So r equals 2 sine of 4 theta. Okay, so notice I have 8 petals, okay, none of which are on any of the axes, but I have 2 in here, 2 here. Notice they're all equally spaced. If I have 8 petals, well, I would have to have 360 divided by 8 would be the number of degrees in between all of these. So let me just do that quickly on my calculator here. Let's kind of go to a scratch pad. And 360 divided by 8, 45 degrees. Okay, so there's 45 degrees between each of the points in my graph. So 45 degrees here, 45, 45. So that means there's going to be 45 from here to here. 45 is pi over 4. So this is going to be half of pi over 4, which is pi over 8. Okay, no wonder I couldn't find it. Pi over 8 is not a special angle. That's kind of hard to try to find. So this turns out to have my first petal at pi over 8. And I'm going to have to kind of estimate where that is. So maybe kind of like this, and another one that's kind of like this. Maybe. Okay, sort of like that. All right. So notice I'm not really being terribly picky about what exactly that angle is. As long as I know where the first petal is, I can just sort of estimate where the other ones are. And that's fine. I'm not asking for perfection on this. What do I actually want to know about these? I want to know location of the first petal. So location of the first petal. I want to know length. And I want to know number of petals. And then you just make them evenly spaced, kind of eyeball them from there. Okay, let's look at 2 sine of 5 theta. Now, notice how 4 theta gives you 8 petals. 5 theta should give me 5 petals. And we should have a line of symmetry that is vertical here. So let's look and see what that would look like. So 2 sine of 5 theta. So notice we have a vertical line of symmetry, so we do have one petal going straight up. But the first petal in quadrant 1, where is that exactly? So once again, if this is pi over 2, I could take 360 divided by 5 and figure out what this angle is. That's probably going to be my best bet to kind of estimate where that is. So let me do that on my calculator. So 360 divided by 5 petals. Okay, 72 degrees apiece. So notice I had one sticking straight up, so 90 minus 72 gives me 18 degrees. Well, 18 degrees is 1/10 of 180, so that's going to be pi over 10. Okay, so I'm going to kind of show you how I got these. So this is 45 degrees. Actually, let me kind of make this a little bit less intrusive. So from here to here is 45 or pi over 4. So from here to here is half of pi over 4, which is pi over 8. So that's how I figured that one out. Now here I have one petal sticking straight up, and then I have another petal kind of an angle here, another petal sort of down here, another sort of down here, and another sort of like this. Okay, so once again, I'm not being terribly picky, but I know that these angles are 360 divided by 5, or 72 degrees apart. So that means that this is 18 degrees, because 72 plus 18 is 90. 18 is 1/10 of 180, so it's pi over 10. So the angle of the first petal here is pi over 10. So let's look and see if we see a pattern here. When we have when b is 2, we have pi over 4. When b is 3, we have pi over 6. When b is 4, this is pi over 8. When b is 5, we have pi over 10. So it looks like, in general, that that we have the location of the first petal. So b is equal to 2, pi over 4. b is equal to 3, pi over 6. b is equal to 4, pi over 8. b is equal to 5, pi over 10. So this is pi over 2b. Now, why is that true? The reason that's true is that the sine of pi over 2 is equal to 1. That's the biggest value I can get for sine. So that's where the tip of the petal is going to occur. So I want b theta to equal pi over 2, which means theta, if I multiply both sides by 1 over b, then that means theta is equal to pi over 2b. So that's the reason why that works. Now, the other thing I need to know is what happens when I make a or b negative. So looking at a graph with an odd number of petals, which we have up here, what happens if I make a negative? Okay, predictably, every petal goes the opposite direction. So the one that's sticking up goes down. The one that's in quadrant 1 flips to quadrant 3. The one that's in quadrant 2 flips to quadrant 4, and so forth. So there's where it looks like that. It has the appearance of turning the graph upside down, but it's really every petal reflecting 180 degrees. Now, what happens if I make 5 negative? Interesting. It has the same effect as making the a negative. So when I make b negative, it affects the graph as the same way as a. So let's think about this. So if I have, and I'm just going to give an example where we have 3 petals because I think that would be easier to draw. So let's look at the one with 3. Okay, so here's looking at the second example. So r is equal to, let's say, 2 sine of 3 theta. So it looks like this and this and this. So if we make it r equal negative 2 sine of 3 theta, then it's going to look like this. And if we make b negative and we say r is equal to 2 sine of negative 3 theta, it's also going to look like this. Why is that? It's because sine is an odd function. In an odd function, sine of negative x is equal to negative sine of x. So that means if I have sine of negative b theta, let's make it with an a there, a sine of negative b theta is the same as negative a sine of b theta. Okay, so they act exactly the same way, whether we make it negative inside the function or outside the function. Okay, so there are your sine polar roses.